Welcome back, everyone. Looks like it's the official time once again. We're now on week 15, and for meeting 4 times a week, we've definitely been through a lot. What we're going to do today is just finish off section 12.3. I kind of misspoke there. I think we'll most likely finish that on Tuesday's class. After Tuesday's class, we'll turn over to reviewing for the final exam, starting with the top document here, review of inferential methods, and then we'll take a look at the other problems as time permits. Also, I felt like we need to make a small change with the WebAssign. The due dates were December 11th for all work in WebAssign, but I felt like that didn't really make sense. This section we're probably going to finish on Tuesday, and a week from Tuesday is December 12th. So I made everything officially due on December 12th on WebAssign, just since that would give us the normal 1 week turnaround time for completing a section. No reason to change that all of a sudden. So that's where we're at so far, folks. Any questions or comments before we get started? Okay, well, we're nearly done with the course. That's really kind of exciting. Just one last section to take a look at, hypothesis testing, and then we'll be there. So let me open up the main notes. We took a look at these notes towards the last part of class when we were here on Thursday last week. We didn't have enough time to get very far into any of these. We just kind of looked at them. But now we're going to take a closer look and start working through some of these problems. To start, the major formulas for the whole procedure are really right here. The test statistic T we'll deal with, since we're dealing with now numerical data. It'll involve the statistic X bar, subtract the hypothesized value mu naught, so we're looking at a distance. And because we're dividing by the standard error of X bar, this will be, once again, the approximate number of standard deviations. The sample mean X bar is away from the value of mu taken from the null hypothesis. Just like in chapter 10, our first thing to do here is assume the null hypothesis is true and see just how compatible our data is with that assumption down there. But now we're dealing with numerical data. We're dealing with degrees of freedom, the t distribution. And so we have this new object to calculate. Not too bad of a formula. That's about as nice as it gets. Degrees of freedom with sample size n-1 will tell us which t distribution we're going to look at in order to get our p-value. As far as the p-values go, I felt like we should do this again because it's kind of informative to see it a second time. But the actual graphs I'm going to plot here are no different from section 10.5. There is one difference. I made a revision here. The changes are in red. I forgot that this is t. I put it in as z first. Sorry for the confusion with that. Because we're dealing with numerical data, that should read as a t. I think I typed this out or made this revision on December 4th. So if you change all the things here to t, it looks like 5 different things. Sorry about that. It was all over the place. Then you're in good shape. Any questions at the moment, folks, before we take a look at the p-values? Okay, well, we won't go to the normal curve. We're using the t-curve. So maybe the first thing to take a look at is, where do we go in the calculator for a p-value? We would still hit second and bars to pull up the list of probability functions. And now go down to t-CDF. This will be the function that we'll actually use to get our p-values. And good news for folks with the TID3, you also have a t-CDF function as well. So all the calculators that are typically used are supported here. So that's where the t-value comes from. But over here, it's helpful to have a picture. All this is going to be based off the t test statistic. So let's give this a important looking color. It is important, so our graph will start off by looking like this. So this is the t distribution. Degrees of freedom is n-1. Typically, you'd have a number right here, but since it's a formula, I'll just leave it as n-1. As a reminder, that does go into the calculator. Then we calculate our t-test statistic. Here's t right up here. And whatever this value comes out as, it could be positive or negative. I'll place it over here. So we have a t-test statistic in this location. That will definitely vary on problem to problem, but for just a visualization, let's place it here. And then all of this area is the p-value. So the p-value will be equal to the probability that t is less than the test statistic value. So if this was, say, a -3, we calculate the probability that t is less than -3 to get all this area here. So that's our right tail test. For the left tail test, it's almost the same exact picture, things just flip around. So in the left tail test, we'd be looking at something about like this. 0 would be located here, degrees of freedom still n-1. Redundant, but that's always a good process to get in the habit of. And if it's a left tail test, our hope is that our t-test statistic is really far out here. But again, it could be anywhere, and we're taking the area to the left. I'll place it here to make it look like significant in this case. So this is where t comes out as. All of that area is now finally going to be our p-value. And as a probability function, it'd be the probability that t is less than the test, I'll write stat for short, value. So once again, if this was, say, -2, you just calculate this with a -2 on the left. Then the two-tailed test is the trickiest one. But any questions so far, folks, to this stage? Yeah. Oh, absolutely. Thanks for spotting that. I'm confused too. Yeah, this greater than should have matched that direction there, which is the best way to think about it. So greater than in that location, and I think that's a highlight worthy spot right here. And yes, absolutely. Thanks for fixing the notes on that spot. Yeah, definitely weird. So let me highlight here to here just to convey the mistake and the right way to think about it. Match the directions in your alternative hypothesis, and you're on the right track. Again, thanks for fixing that. Other questions at the moment? Okay, last up is the two-tailed test. I figured for this time, it might be a good idea to just draw out one graph and then put in two descriptions, depending on what happens to the test statistic. So we'll have 0 here, degrees of freedom, and -1 like before. Then we're going to have two values for t, but it could either be positive. If t is positive, we put a value here and get the area to the right. But even if t is positive, we would go over here and negate it and also accumulate the area to the left. So this formula is tricky because your test statistic t, well, didn't mean to highlight the whole thing. Your test statistic t could be either positive or negative, but we want both of these areas no matter what t is. So let's write out here. Let me see if I can put in just a little bit more space. No, I cannot. It's really kind of tight. If we page up a bit. There we go. So if we put, say, t, let me put it over here. If t is positive, then we'll have to double this area. And if t is negative, we'll double that area. So t negative, double this area instead. So that's the setup for the p-values that we're going to be getting. And again, the only thing new is we're using, oh, the calculator turned off. We're using TCDF, so option number 7. You know, we might as well put that on the notes. Use option 6. Yeah, thanks for spotting that. I don't know why I thought that was 7. Option number 6. TCDF. If you click that option number 6, it's going to want the lower and upper degrees of freedom, and that's it. So we'll look at these kind of diagrams. I'll still draw them out when we're doing the p-values, just to indicate where the area is going to be, what the lower upper value should be, and so on. And this is the full description finally for doing a hypothesis test for numeric data where you have means instead of proportions. Yeah, go ahead. I might have said that. I think I might have said something along the lines. It's all in the video, so we could always go back and watch those videos. I think what I might have said was whatever happens with 12.3, we don't get it finished this week, it won't be on the exam. If we can get it done on Tuesday, Thursday, wherever we end up on, that will probably be on the exam.
There's no quiz on this, either we just need to know it for that.
Exactly, yeah. Other questions so far? Yeah. The trouble with that is if I label, say, this one is T, we're gonna hurt. Yeah, we could put a T here and a T here. I just think of this one as being the negative one, this one as being the positive one. Yeah. Other questions so far?
We might get to it, I don't know if I'm jumping ahead, but when we did the upper and the lower numbers, are we still gonna be using the negative 10 to the 99th power and the positive 10 to the 99th power?
Yes, we will, absolutely. Essentially, every time you do a hypothesis test, you'll always be using one of those.
Okay.
And it wouldn't be bad to add to the notes right here. If you're doing this version, the right tail test, your lower is going to be equal to negative, or excuse me, the lower is going to be equal to your test statistic T, and your upper, that was weird, that changed in a weird way. Your upper on this one will be positive 1099. So each and every time you do a right tail test, that's a foregone conclusion. I'm glad you asked that question. That's not a bad thing to add to the notes right here. I think this helps a lot. So for the left tail test, your lower will be equal to negative 10 power 99. Your upper on this one will be the test statistic T. And this one's a little bit more complicated because it'll depend. If your T is negative, then your lower equals negative 10 power 99, and upper would be the test statistic T. But the biggest thing to worry about is you have to double that area. So you'll get a value from the calculator, multiply it by 2, and you're in good shape. If we're in this location, T is positive, then we'll say lower would be equal to the test statistic T on this one, and upper right here.
Yeah.
Well, it would be, well, the thing that we're doubling wouldn't be the test statistic, it'd be the actual area itself.
So we're gonna double that upper.
Well, the upper is still going to be 10 power 99 on this one. So upper equals 10 power 99. And let me show you what will happen essentially with the double. Let's imagine we had a positive T. Let's just calculate one just to visualize it. So if T was maybe a 2.3, then the upper is going to be 10 power 99. Degrees of freedom, let's just give it a random number, maybe 30. Sample size would have been 31. So this, hang on, negative. I'm not too sure how I got a negative answer on that. That should have came out positive. We're trying to get an area. Let me try one more time. Second bars, we're going to TCDF, much like, say, if it was normal CDF. And I put in lower is going to be a 2.3. Upper is 10 to the power 99. Degrees of freedom is 30. And no idea what happened on that line. This is an emulated calculator. Must have been just a memory issue or something. We have this as the area, but that's just this area here. When we say double it, we go in the calculator times 2. Exactly. So we doubled the answer after we run through TCDF.
And you do the same thing if you do it for the lower.
If it's a two-tailed test, yes, exactly.
You would wait till after that.
Exactly, yeah. So on all these, we use whatever T comes out as, but the doubling happens on the two-tailed test afterwards. Exactly. Yep, you betcha. Thanks for asking those questions. Other questions or comments so far, folks? Okay, so this is pretty much it. This is the hypothesis testing. If we have numerical data, our goal now is just to practice what we have down below here in the document. So let me scroll down. Well, maybe before that, here's this same table and reminder now. The way we're going to determine if we reject the null hypothesis or fail to do so is by how small the p-value is. If it's less than alpha, we consider this to be a small p-value and we'll reject the null. But if it's bigger than the significance level alpha, whatever it's specified, or we might specify it, then we'll fail to reject that null hypothesis. And we'll just say the study failed to find significant evidence that the alternative is true. So this table is directly copied from section 10.5, which is pretty handy. Now, with all that information, we're ready to get started with our first test. Looks like this one's coming from the medical sciences, and it says to start out, the ankle brachial index, we'll paraphrase that as ABI, compares blood pressure of a patient's arm to the blood pressure of a patient's leg. So I guess we're looking at some kind of difference between the two. The ABI can be an indicator of different diseases, including arterial diseases. And they say here, a healthy ABI is 0.9 or greater. Let's highlight that. Anytime they tell you specific extra information that has a value, that's probably going to be used in the problem some way, somehow. Not a guarantee, but something worth highlighting. So after that context, they tell us, in a study by McDermott titled Sex Differences in Peripheral Arterial Diseases, the researchers obtained the ABI from a random sample of 187 women with peripheral arterial disease. So we have a sample size. We have N is 187 women. So N equals 187. Next, they tell us the results were a mean ABI of 0.64. Now they're giving us some summary statistics. In our own notation, we'll write X bar is 0.64. So that's the mean and ankle brachial index. And we have a standard deviation of 0.15. So let's write in sigma, or excuse me, not sigma, S. These are statistics, not population characteristics. S is 0.15. They even give us more. Now they say at the 1% significance level, here they're giving us the value we typically write in as alpha. So let's put in alpha as, it's best to convert this from the percentage to a decimal number, so 0.01. Now they ask us the question, do the data provide significant statistical evidence to conclude that, on average, women with peripheral arterial disease have an unhealthy ABI? That's definitely a research question, and that's confusing. Let's highlight maybe here. Women with peripheral arterial disease have an unhealthy ABI. From the top of the problem, they said a healthy ABI is 0.90 or greater. So if they're saying an unhealthy ABI, what we're really saying is less than 0.9 ABI. So this one is really a left-tailed test altogether on the way they pose the question. Well, any questions or comments, folks, so far? Okay, well, now that we have the rundown of the information of the problem, it says, describe the unknown parameter using the context of the study. So in this problem, the parameter is going to be mu. And the reason we know is the moment you see X bar is an approximator of the unknown population characteristic mu. So that must be the right thing to put here as a symbol to start. We can say next that mu is equal to the mean ABI. ABI has to be there some way, somehow, because all these values are 0.64 for the mean ABI, S for the standard deviation ABI, and so on. So it's the mean ABI of all women, but we don't mean necessarily all women. We mean all women with a specific condition. Here in the question it said women with peripheral arterial disease, so that has to be here in the context as well. So the unknown population characteristic or parameter is the mean ABI of all women with peripheral arterial disease. My penmanship is really bad today with all the excess coffee. Let me know if anything is unreadable and I'll definitely fix it. But now we have a population characteristic or parameter. We can state hypotheses and run through the procedure. Again, often this is the hardest part here to nail down exactly the way we want. Does that look all right to folks so far? Okay, and even though I keep on saying this is probably the hardest part, I notice people are getting definitely much better at this, looking at quizzes and old exams and such. So congratulations, we're getting through this nastiest part of the course in a certain sense. Next thing we need is hypotheses. When it refers to the null hypothesis, it'll look like this. H naught mu equals I'll leave this blank for a moment. If you know the value now, don't hesitate to call it out. HA is for the alternative hypothesis, and it will go mu, like before. From here, they're asking if women have less than 0.9 ABI for it to be unhealthy. So this turns into a left tail test with a less than right here. Other things we could put here, even though it's not strictly required, it's a helpful reminder. I usually put alpha on the same line I state the hypotheses, 0.01. But now we need to figure out what goes here and what goes here. Oftentimes when you do these problems, it's a good idea to read through them multiple times. Read them once, gather some information, maybe write down the characteristic, read through it again to make sure nothing's missing in the population characteristic, and then maybe read through it even again if you notice something's missing. We missed one thing, the value to be tested, which would go here and here. Has anyone spotted what it would be? Exactly, it's the 0.9, which is the value in question. Having less than the 0.9 means we're dealing with the unhealthy ABI, and they're just wondering, do people with peripheral arterial disease have less than 0.9 ABI? So that's the mu naught equals, I think we usually use a slightly off blue color for that. Here's the mu naught equals 0.9, coming from either here or what was said below. Once you have this value, this is really critical. It's going to go here in the null hypothesis, 0.9. And finally, we'll go here in the alternative hypothesis as well, 0.09. And notice without that, we can't even make the correct practical interpretation, because if we reject the null, we have to interpret this statement right here with the 0.9 going along with it. Yeah, go ahead.
That's so decimal behind.
Oh, geez, it definitely is. I'm not sure what I was doing there. Thanks for spotting that. This is a 0.09. That's probably really bad ABI index. We're testing 0.9. A little bit more down to earth. Thanks for spotting that. Other questions so far? Okay, with that done, this is kind of an interesting question, because this one can be tricky sometimes, because it feels like we're doing a lot more than we really are. But if this was a confidence interval problem that you might see in the final exam, it's still just the same. Degrees of freedom is still the formula, sample size n minus 1. So we look up our sample size at 187 women, reduced by 1, and degrees of freedom are 186 in this problem. It's almost deceptive because it feels like we're doing a whole lot more, but this is, again, kind of a way for me to assign partial credit. I don't know essentially exactly what's going into your calculator unless I know your degrees of freedom. So now that we have that, we're down to the standard error next. Usually we color code the standard error in green. And in this problem, you could call it just SE for standard error, but it pays to be sometimes descriptive because we have like 3 different formulas for standard error so far. We're doing the standard error of, if you see a mu in your hypotheses, it would be for the sample mean X bar. Then the formula becomes S divided by the square root of the sample size n. So really, we're just starting to substitute in values and throw things into the calculator at this stage. S from the very top up here is at 0.15. We're dividing by the root of 187. So now in the calculator, let's see what this comes out as. 0.15 division by the square root of 187. Looks like we want 4 decimal places, and to the 4th place, this one is going to be rounding with carry, my least favorite rounding, 0.0110. So we've got it, folks. That's our standard error. I'll keep the 0 here just as a reminder to me and us that we did really round it to 4 decimal places. It rounded to 0 in that position. That look right to folks on the rounding and the otherwise? Okay, with the standard error down, we're one step away from the test statistic T. T is going to be calculated, and I think we used purple on this one as well. As a formula, it goes T equals, first it's the sample mean X bar. It's a shame Microsoft doesn't let us have more than 3 colors. We need like 5 different colors, it feels like. So take X bar, we're going to subtract from that the hypothesized mean, or the mean to be tested. It's referred to as mu naught in the formula, but they're just talking about this value here, the 0.9. And then the whole thing is divided by the standard error of X bar. So SE X bar for down below. Now we're just throwing in a whole bunch of values. So standard kind of substitutions. Going left to right, top to bottom, first hits X bar at 0.64. Subtract from that mu naught. That was the 0.9 coming here in the null hypothesis. So 0.9 in this location. Divide by standard error at 0.0110. So as a formula, this is all we have to calculate. Really, the only danger with this one is be sure to include parentheses around your numerator if you're putting it in as one line. So it should look like 0.64 minus 0.9 division by, I'll use the approximated value, but if you're going for something extra accurate, hit second negative sign, and now you're using this last value up here. Actually, the calculator is using this and just recalculating everything from scratch. It's not rounding at all. But if the problem said to round at this stage to 4 places, you're never doing it incorrectly to round here as well. I'll go with 0.0110. And here's our test statistic T. Notice how many standard deviations the sample mean X bar is away from the hypothesized mean of 0.9. And we might have noticed that the sample mean is very, very small in this problem relative to the hypothesized mean of 0.9 for ABI. And so this is one of those problems where we almost don't even need a p-value. Our calculator is pretty much going to either give us scientific notation or it's just going to give up and give us a 0. We'll see what happens. But let's put in to 4 decimal places. This turned out as negative 23.6364 upon rounding standard deviations. So our data looks extremely significant. This is probably the most significant set of data we've encountered. But we'll find the p-value just to show how significant really. Any questions so far, folks, on our test statistic? That's a hard word all of a sudden. Okay, so for the p-value, this is going to be the probability that T, our test statistic, before we get too far, we go up to our alternative hypothesis. This one's a left tail test, so we'll have a less than here as well. And this has to be less than the value we just found, negative 23.6364. So let's close that off. And here's a quick graph for what that would look like. I won't ask you to calculate the graph or to produce the graph, but it's helpful that I'd say go for it. Definitely helps me out. So let's put this in. Degrees of freedom is from part C, we found 186. The test statistic T is really hard to plot on this. It's so far to the left that I cannot plot it accurately. I'll just emphasize it's far, far away to the left by putting it way out here. T equals negative 23.6364. Now, all this area here is going to be our p-value. But this is a new distribution, TCDF, that we have to use. So let's indicate this here. Use TCDF. Then input 1 lower is going to be negative 10 to the power of 99. Input 2, the upper, is just T that we found. And the third input is the degrees of freedom. So that's all that needs to go in. And let's see what the calculator is going to do with this. You have to remember this is a finite machine, and this is extremely far to the left. This is almost like astronomically far away. So the calculator might not be able to give us something positive. Let's give it a try. So second, bars, option 6, TCDF. If you just click 6, you save a few clicks on your calculator. The lower is negative 10 power 99. And the upper value is negative 23.6364. Still needs a degrees of freedom. It's at 186. And when we put all this into the calculator, here's what it says, 0. Now, it's not really true that it's 0. It's really a positive quantity. It's greater than 0. But occasionally, when these are so far away, this is the best the calculator is going to do. If you give 0 web assign, that would be the correct answer. Sorry, question first.
Oh, sorry.
Oh, no worries. And if you want to copy the instructions to the letter to 4 decimal places, this is 0.0000. Looks silly, but that's not a bad thing to put down. And just for the emphasis of what's happening in the calculator, let me show by going back to second bars, TCDF. Let's suppose this was, say, a negative 5. Now that's still extremely large in the sense that it's away from 0 far, far away. If it was negative 5, it would look like this in the problem. You'd start to see exponential notation. This one is still rounding to 0.0000 altogether. But what happened with negative 23.6364 is the order of magnitude is so large, the calculator is giving up. It can't calculate numbers that small, and so it just outputs a 0. So if you ever see a 0, but your test statistic looks like this, either positive or negative, you are on the right track with that problem. So we have a p-value that's essentially 0. Now, here's a portion where we have to make a decision. Any volunteers in the class? Is this rejecting the null hypothesis, or is this failing to reject? Exactly. Let me put down exactly what you said. So the p-value is 0.0000, which is less than 0.01, which is equal to alpha. And this implies right away, reject H0 in favor of HA. So we can't tell people that since not everyone likes this kind of language. This is pure statistical language. But our job as statisticians is more than calculating this. It's communicating our results to the general public, which is the harder step. And that's the practical conclusion we see down below. So we have to say what was written down in orange exactly for the context in our problem, but it's really not too different from what we've done before. We go up to the top. We're going to need our hypotheses, the alternative specifically, and we're also going to need the population characteristic. So all of this right here, let's grab alpha just because we can, just for emphasis. But all that is really what we need to conclude on this problem. Any questions, folks, so far? Okay, in this situation where that is, again, an astronomically large amount of standard deviations, that the sample mean was away from 0.9, it's not a bad idea to say words like this. We have overwhelming statistical evidence to support the statement or the hypothesis. I'll go with the statement that, and now let's look up the statement. We're thinking of this one down below here. So we just read out mu, the mean ABI of all women with peripheral arterial disease next we just are going to say is less than that 0.9, 0.9 ABI. So there is a great deal of evidence to say the statement is true. And who would be really interested in this statement? Probably doctors, physician assistants, things like that, because now they know they have an expectation. If someone has peripheral arterial disease, they probably have an unhealthy range of ABI as well. And so they can now conflate the information together. If you see someone with this particular disease, probably check their ABI as well to see if that's also a problem. And the insurers would probably approve that with the conclusion here on this test. Well, any questions, folks, on that rundown for hypothesis testing? Okay, well, we did it. That's the end of that problem there. All we're going to try to do next is, let's see, we have a few minutes. Let's give one more a try, and we'll consider this to be really the last official problem for the entire course. Everything else is going to be reviewed right after this one. We'll probably finish this one when we come back on Tuesday's class. So let's take a look. It starts off by saying, acid rain from the burning of fossil fuels has caused many of the lakes around the world to become acidic. The biology in these lakes often collapses because the rapid and unfavorable changes in water chemistry takes sometimes centuries for organisms to adapt to small changes. They say next, a lake is classified as non-acidic if it has a pH greater than 6. That looks important, so let's highlight that right there. Like in the other problem, it's not a guarantee that we have a hypothesized mean from here, but we should definitely start looking, so that's highlight worthy. It goes on to say for the next portion, Marchetto and Lamy measured the pH of high mountain lakes in the Southern Alps and reported their findings in the paper, Reconstruction of pH by Chrysophian Scales in Some Lakes of the Southern Alps. They tell us the pH levels obtained by the researchers, a random sample of 15 lakes, are given below. Well, they tell us the sample size. Let's double check. They said 15, 3, 4, 5. Yeah, I thought that was a row of 6. That does look legitimate. So let's put down sample size n is 15. And we did have to do this in another problem where sometimes numerical data is given and they don't give us the statistic. Occasionally we have to calculate that ourselves. But this one, they just gave it to us. So let's take it and run with it. The sample's mean is 6.60 and the sample's standard deviation is 0.67. Next, it says at the 5% significance level, from there we can indicate alpha is 0.05. Let me highlight that just to show where we grabbed that from. So at 5% significance level, does the data provide sufficient evidence to conclude that, on average, high mountain lakes in the Southern Alps have a pH different from 6.35? They gave us a couple of good pieces of information here. When they said different from, that's both directions. We're testing if it's above or below 6.35. So we're going to do a two-tailed test. So from just right here, this is a two-tailed test. It's definitely always kind of concerning when one single word can absolutely change the whole problem goes down. But these are pretty standard kind of keywords. I won't be kind of disguising them on exam. So look for things like different from, always to indicate two-tailed test. So we're seeing if it's different from 6.35. That means the value of the mean to be tested is mu naught equals 6.35 in pH. That's kind of curious. Up here, they're talking about acidic is greater than 6. But down below, we're looking at 6.35. Where did that come from? No idea. Probably the experts who work in high mountain lakes, those biologists, figured around this figure, things start to become a problem if it's different from this value. So we got it, folks. That's the rundown so far. All we now need is the unknown population characteristic or parameter. It's indicated in the notes. This will be mu again. And let's think about this one slowly. Because we are dealing with numerical data, that's a pretty big giveaway if they just give us the data values, or if you see a mean. You could start off by writing mu is equal to the true average. And there's a lot of ways to say this. You could have said the population average or the population mean. I'll go with true average. Either way, you're still saying the same exact thing. We're talking about a population. And so you have to say the average of what? The moment you said average, you're talking about the 6.60. It was the average of these values. So we have to say, well, what were those values? They were pH quantities. So we can say pH of high mountain lakes in the Southern Alps. We essentially just work backwards. We look at the data, see where it came from, and carry in this context. Mu equals the true average pH of, this is an important word to say here. We're talking about all of the high mountain lakes, not just this 15 in the sample. So of all high mountain lakes, in the Southern Alps. We got it, folks. That's our population characteristic mu. Does it make sense on how we put that together? Okay, now that we've got mu, we're pretty much home free for the null hypotheses, or the null and alternative hypotheses. H naught is going to be indicated as a mu equals, and the value we set it equal to is the value to be tested, the 6.35 pH. So that's our null. Next, we go to our alternative, HA. This will be a mu. It compares it against the 6.35 again. But then we go where it said different from. Because this is now all of a sudden a two-tailed test, in the middle, we put in not equals. That means we have to take some care when we go to calculate the sample, or excuse me, the p-value on this one, because we will be doubling a probability to get the right values. So that's the tough part of the problem. All we now need is degrees of freedom, test statistic, and we could get a p-value in pretty short order after that. Any questions so far, folks, to this stage? Okay, let's do the degrees of freedom formula. df equals n minus 1. Up here, sample size is 15. Minus 1, so just 14. And honestly, if you put just this on your paper, that would be okay. Degrees of freedom is a pretty simple formula, but I'm putting out the whole expression just for a paper trail in the notes. When it comes to other things like, say, standard error and test statistic, I would say for these ones, even though you wouldn't lose points, it's definitely a good strategy to write down the formula first. It helps with memorization. And when everything's lined out in front of you, it's much easier to see where things go, how you make the substitution happen. So for this portion where it says standard error, Let's work this one out carefully and just indicate the formula to start. SC of X bar is S divided by the square root of N. Now that that's all laid out, we can say that it's equal to, go back to S, it's at 0.67. And we're dividing by the square root of 15. One thing that's kind of an easy mistake to make, I've made this mistake myself several times, is you have the sample size of 15 up here, the degrees of freedom 14 over here, and I don't know why, but for me, it's really tempting to put in that n, maybe because I'm looking at that 14 like this, 14 there. That's a sad way to lose the whole problem in WebAssign. On an exam, you might lose just a little bit of partial credit, nothing too major. Okay, but with this all in play, now we can now calculate this. We want 4 decimal places of accuracy. So it's a 0.67 divided by the root of 15. So we have another rounding with carry. So this is 0.1730 after rounding. Now that the standard error is out of the way, the t test statistic is a fast computation. I didn't notice this before, but that formatting actually looks wrong. Should look more like this, a legitimate hyphen. Not a major typo, just looked funny. First thing to do on this one is write it down as a formula. The test statistic t is given to be, first we take the sample mean, X bar, see how far away it is from the hypothesized mean. That came out of the null hypothesis, 6.35. Struggling with my decimals again, let me try again, 6.35. And we want to know how far away the sample mean is away from the hypothesized mean in terms of approximated standard deviations, standard errors. So that's the process. Next, we just plug in the information. Above, X bar was given to be 6.60, so that would go right here. Then we're subtracting away 6.35 and divide the whole thing by standard error, which is 0.1730. So next, go back to the calculator and let's just type this in as 6.60. Don't know if the 0 matters there, but at least we're copying it verbatim, 6.35. And then division by 0.1730. So altogether, that's our test statistic. At 4 decimal places, we have 1.4451. So this is almost 1.5 standard deviations away from the hypothesized mean, the sample mean from the value 6.35. That means, well, we might not reject the null hypothesis this time. This is probably going to be a pretty big p-value. On one end of the extreme, that one is crazy, negative 23 standard deviations. But here, this starts to look typical. Well, we still have some work to do. We want to do the p-value next, give a practical conclusion. But this is the easier steps right here, at least. Any questions at all, folks, before we end the notes here today? Okay, when we come back, we'll finish off this problem and then convert to reviewing for the final exam. Looks like we'll have just about 3 days to do so. Well, have a nice night, folks, and I'll see you all on Tuesday's class. Thanks.
Thank you.
Sure.